So we are starting chapter, oh, how about I present my screen? Would that be good? So y'all can actually see something. Go ahead and make sure your phone is put away and that you are focusing on this. If your TV is on, I suggest turning it off so you're not distracted. Make sure your camera is on. I can see you, see your face, make sure you're understanding what I'm doing. Okay. So 7172, it's exponential functions and graphs, exponential functions and graphs. So we have a new type of function. We've done so many functions this year. Quadratic functions, square root functions, what other ones? Absolute value functions, cubic functions, linear functions. Now we're going to do exponential. The root word in exponential is exponent. We're going to have the variable in the exponent. That's what makes it an exponential function. The variable is going to be in the exponent. I'm going to write down what it looks like, and then I'll show you guys how to graph these particular problems. You would have done this basic first part in Algebra 1, but you might have forgotten it's been a couple years. So we have a number times a base raised to the x. It looks kind of like your geometric sequence formula, doesn't it? Kind of, except that we had an n-1 right there, but it's the same general idea. Your a value, or your number in the front, this is your initial value, your starting value. And on the graph, that shows up as your y-intercept. Is that how you spell initial? No, there we go. Nope, that's not it either. Try again. So on the graph, this number here, if there is a number in the front, that is your y-intercept or your initial value. If there's not a number there, we haven't understood 1, your initial value or your y-intercept is 1. Okay. And B stands for your base. And just like with your geometric sequences, it's what the numbers get multiplied by each time. So if there were a 2 there, your numbers would be doubling. If there was a 3, what would they be doing? Tripling. If it was a 4, your numbers each time would be quadrupling. Okay, so this is where you start, and this is what's going to be happening to your numbers each time, what you're going to multiply by. This is our base. Or we can think about it as our ratio that we're multiplying. If our base is more than 1, our numbers are going to be going up, right? If I'm doubling or tripling, aren't your numbers going to be increasing in size? They get bigger in size. Yep. If it's more than 1, we're going to be growing. So this is going to be a growth problem. So if your base, we have 2 things that can happen. If the base is more than 1, we have a growth. That would be something doubling or tripling or quadrupling. If your base is between 0 and 1, that's like a half or a third, our numbers would be getting cut in half or getting cut in thirds or getting cut in fourths. Is that going to be getting bigger or smaller? If something's getting cut in half and then cut in thirds and then cut in fourths, what do you guys think? It's going to be getting smaller. So we call those a decay. So if it's between 0 and 1 for your base, that is a decay. So just think about this number here as your ratio like you did with the geometric sequences. Is it getting bigger? Is it being multiplied by a whole number or something that's more than 1? Is it getting smaller between 0 and 1? Okay. All right, we also, before we draw some of these graphs so you can see it, we have a fancy number that we use all the time with exponential functions. It has special properties, kind of like pi does. You know how we use pi when we're doing circles and triangles and stuff? It just has special properties. With exponential functions, we have a letter E. Okay, that's like our natural exponential number. We use it all the time. And E by itself, let me see what the actual technical numbers, it's 2.71828. There's a lot after that. So it's an irrational number that shows up in exponential and logarithmic functions. We'll do logarithms in a couple days. It's our special natural exponential number that gets used. It gets used so much that it has its own symbol, which is the E. So if you see E, don't think, oh, that's crazy. Just in your head, remember that's 2.718. Okay. So if E were a base, would that be a growth or a decay? If E were the base, would that be a growth or decay? Is E more than
Decay.
1? 0 and 1. E is 2.718. Is that more than 1 or between 0 and 1? It's more than 1, so that would be a growth. Okay. So if E is a base, that's a growth. Sometimes you see 1 over E, and in that case, that would be a decay because that would be 1 over 2.7, which is kind of like a half or a third. All right. So we're going to look at a problem. I'm just going to write it down. I want you guys to tell me what the y-intercept is and what the base is, and then if it's a growth or a decay. So I'm just going to write a problem, and on your paper, tell me the y-intercept, the base, and if it's a growth or a decay. I'll do 3 of them. I want you to try all 3, and then we'll see. So tell the y-intercept, the base, and if it's a growth or a decay. Okay, when you think you've got them all, hit your raise hand button. Okay. All right, so I want you for the first one, for the 5 times 2 to the x, just separate them by commas what your answers are. So what do you think was the y-intercept, comma? What do you think is the base, comma? What do you think if it's a growth or decay? So just for part A, just put that in the chat. Y-intercept, comma, what's the base, comma, is it a growth or decay? Good job. Everybody's putting the same thing. The y-intercept is 5. Its base is 2, and it's a growth. So that starts at 5, and it's doubling every time. Okay, so I start at 5. What would my next number be that I would be plotting if it's doubling? It would be 10, right? And then after that, what would be doubling 10? 20 would be the next number. So if you're looking at the graph, to try and find the graph, if I wanted to graph this, I would start at 5. That's my starting point. 1, 2, 3, 4, 5 on the y-axis. And I'm doubling every time. So as I go over to 1, I would be at 10. 1, 2, 3, 4, 5 more. Be at 10. And then if I was going over to the next one, I would be at 20. Okay. And then what happens is if you were going in the backwards direction, I would kind of be cutting those in half if I was going backwards. It's like this. So it looks kind of like this as a graph. It's never going to be below 0 for this graph because there's no way to get a negative number. If you're doing 2 to a power, it doesn't matter if it's a positive or negative power. There's no way you can get a negative, right? Does that make sense? A positive times a positive raised to something, a negative's not going to pop up. So we're never going to get that, and we're never going to get 0. So our graph looks like that. That's an exponential growth. Starts at 5 and doubles every time. Okay. All right, for B, let's go ahead and write down what we think for B. The y-intercept, comma, the base, comma, is it growth or decay? So put that in the chat for part B. What's the y-intercept? What is the base? And is it growth or decay? All right, good. Our number in the front, that is our y-intercept. That's our starting position. We're going to start at 1/2 on the y-axis. And then our base is 4. Our base tells us so we're multiplying by 4 each time. So that's going to get bigger or smaller if we're quadrupling it. It's going to get bigger, so that's going to give us a growth. That base is bigger than 1, so that would be a growth for us. So our graph looks very similar to the one that we just drew, except we're not going to start at 5. We're going to start at 1/2. Let's start at 1/2. 1/2 times 4 is 2, right? 2 times 4 is 8. It looks like this. And it also does not touch 0 across the x-axis. So ways for you to determine what the graph is, think where should it cross, and then what's happening every time. It's multiplying by 4, so you would multiply your starting number times 4 to get your next value. All right, on part C, let's see what you guys put down for your y-intercept, your base, and if it's a growth or a decay. Good job for everyone that's been typing that in. Remember, if you don't have a number in the front, just like with our geometric sequences, we have to insert a 1, and then we can talk about y-intercept, and we'll move on to growth and decay. So our 1, that is our y-intercept. Our 1/3 is our base. So we're taking our numbers and cutting them into thirds. Is that going to be a growth or a decay if we're shrinking them by a third? We're getting bigger or smaller? We're going down, we're getting smaller. This is a decay. So if I were to plot this graph, I'm going to start at 1 and become, you're going to shrink every time by a third. It's going to get really small really quickly. So start at 1. Now I'm a third of that, and 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 it gets really, really small. Am I ever going to touch the x-axis? No, because even if you're getting really, really small, I'm still going to have a third of what I started with. So I'm never going to get down to 0. And then it just backtracks as a bigger graph on the other side. It's like making it times 3 times 3 times 3 the other way. Here. So our y-intercept was 1. We're cutting by a third each time. Okay. And on your graphs, if you're kind of stuck, like, oh, I don't know which one it is, which one to match, you can always put these into Desmos and look at it on your graph there. Okay. And you can hover over it and it'll show you some points. Any questions on determining y-intercept base and if it's growth or decay? Thumbs up if y'all are good with that. Okay. Remember, put your phone away. So if you're reacting to text messages by over-exaggerating laughing, go ahead and put that away. All right, the next thing that we're going to look at is we're going to apply this into situational practices. When things are growing or they're doubling or they're increasing by so much every year or every month, we're going to measure how much we have at the end of a certain amount of time. If we start with an initial value and we're growing or we're decreasing by a certain amount each month or each year or each quarter, right? So this is called the exponential model, and it's used when you're talking about interest. You know, when you put money in the bank and then it gains interest over however much time, you can use this exponential model for it. So this first part, the A of t, it's not A times t, it's just like a function value. This is your final amount. Here we have your initial, what you start with. What do you think R stands for? Talking about interest, the interest rate. R is the rate. And it's going to be in decimal form. So if you got a rate of 7%, we don't put 7 in there. We're going to change it to a decimal. Remember, 2 decimal places to the left, that would be 0.07. So we use it in decimal form. And what do you think T stands for? T stands for time. Okay. So the ones that we're going to do today, we're going to have interest that is compounded at the end of every year. So the end of every year, they take the interest that you make and put it back into your account, and then you make money and interest off of that. So how much do you guys want to invest? How much do you want to put in a bank? Somebody type a number in the chat that's more than 1,000. $50,000. Okay, so we are going to invest $50,000. Okay. Let's go with, what kind of interest rate would you like to have? Well, it can be a fake situation. Right now, interest rates aren't that great, but something that's less than 7. Give me a number less than 7. 1, at an interest rate of 1%. Okay. So we have a rate of 1%. And how long are we going to let this sit in the bank and see how much money we're going to make? How many years? Let's do more than 1 year. 4, 6, 8, 5. Let's add all those up together. So that's 15, and then the one from before, 16 years. All right. So we're going to let this sit in the bank for 16 years, and we want to see how much money we have at the end. Okay. The reason that we have the 1 plus the rate in decimal form is because it's going to be 1.01. That's our factor that we're multiplying by. 1 is what we started with. The 0.01 is what we're going to increase each time. And there's a plus or a minus because sometimes your values are decreasing. So if something is depreciating or declining, you use the minus. If it's going up, you're going to use the plus. So let's put it into our formula. A of 16, because we're going to do it for 16 years, is our initial amount. And our initial amount was 50,000. The 1 is always a 1. We use a plus sign because we are increasing. I'm not going to put 1 for my rate. I'm going to put what? What do I need to change it to? 0.01. Okay, good. And this is to the 16 because it's 16 years. So 50,000 times 1 plus 0.01 raised to the 16. I'd say we got a pretty good return. I don't know where my page went. It's disappeared on me. There it is. Can y'all see it now? Okay. All right. So our 1% interest rate for 16 years, we ended up having, did anybody do that on their own? $58,628.93. So after 16 years, our money increased by almost $9,000. So that was $9,000 that the bank just gave you for letting them have your money in the bank for that amount of time. So if we are increasing, we use the plus sign. If we are decreasing, we are going to use the minus sign. Oh, if some of you are starting the assignment right now, I've got to change something on it, so I'm going to have to resubmit it to you guys. So if you're working on that right now, just know that you're going to get, it's going to get redone. So whatever you're doing right now, you're going to have to redo. Just letting you know that, because I made a mistake on the word problems and just realized it. All right, so that is our exponential model. Any questions on how to plug the numbers in and where they go? You guys okay with something like that? Okay. All right. Occasionally we get problems that say that your interest, instead of it being compounded once a year, so at the end of every year, it's compounded continuously. That means that all of the time, your money is making money on itself and then adding that money back to the pile and then making more money on that and then adding it back, but it's doing it all the time instead of what our other situation was where we did it at the end of the year. And for this one, we get to use the fancy E letter that we use all the time for exponential functions. And that's probably why we have it, is because of this formula, the compounded continuously interest formula. The letters stand for the same thing. A of t, that's our final value. The P in this case is the initial value, but another word for initial when you're dealing with money is principal. Principal is what you are putting in at the beginning. Have you heard of principal before when they're dealing with finances? Maybe, maybe not. Principal, which is the same thing as initial. The E is the letter E. There's the button for it on the calculator. If you just type in E in Desmos on your keyboard, it'll come up as the E, and that's fine. And the R and the T are in the exponent position. So this is rate, same thing, the decimal, and then time. We're going to try this one with the same numbers as above, with the 50,000, the 1%, and the 16 years. But instead of our interest being compounded at the end of 1 year, it's going to be compounded all the time. I use this formula, initial, E, raised to the rate time. And if you type that in, we have $58,675.54. We end up having about $50 more than we did in the initial or the original problem. You will always have more money when you compound continuously. Okay. But to know the difference between using these two formulas, if you see the words compounded continuously, you're going to use this. You have to have those words in order to use this formula.